Starship Flight 1-2 was not delayed because the rocket suddenly became impossible. It was delayed because the ground beneath it had to prove it could survive. That is the quiet truth people often miss about giant rockets. The vehicle gets the attention, the engines get the headlines, the flame looks like the event. But for a machine this powerful, the launch pad is not a stage, it is part of the rocket. And if the pad is not ready, the mission is not ready. Flight 1-2 matters because it is not just another Starship test. It is the first flight planned for Starship version 3, using Booster 19, Ship 39, Raptor 3 engines, and a new launch complex at Starbase Pad 2. Almost every major piece is different. Bigger forces, new hardware, new plumbing, new sensors, new failure paths. That is where the delay becomes more interesting than the launch date. From the outside, it looks simple. SpaceX rolls out a booster. It fills the tanks. It fires the engines. Then, if nothing explodes, it launches. But nothing about this system is simple. 33 engines do not merely push downward. They attack the pad with heat, vibration, acoustics, pressure waves, and thousands of tons of force. Water systems have to react instantly. Sensors have to survive violence they are measuring. Valves have to close at the right speed, not just the right time. And one bad signal can stop everything. Not because SpaceX is afraid of testing, because at this scale, uncertainty becomes hardware damage. So the real question is not why Flight 1-2 slipped. The real question is what SpaceX discovered on the ground that was serious enough to make the world's most aggressive rocket company slow down. Most people think a rocket delay means something is wrong with the rocket. A cracked tank, a bad engine, a software issue hiding somewhere inside the vehicle. That assumption makes sense because the rocket is the thing that flies. It is the object we watch. But Starship is not just a rocket. It is a launch system so violent that the ground infrastructure becomes a survival problem of its own. A normal launch pad holds a vehicle. Starship's pad has to endure something closer to an industrial disaster, repeated on command. Cryogenic methane and liquid oxygen move through giant pipes. Water has to appear in massive quantities at exactly the right moment. Steel, concrete, sensors, valves, and electronics all have to keep working while the most powerful rocket ever built tries to leave Earth. And this is what people get wrong. A successful static fire is not just about lighting engines. It is about proving that every system around those engines can remain coherent while the environment turns hostile. The early assumption was that Flight 1-2 was waiting on Booster 19 or Ship 39. Maybe the new vehicle needed more work. Maybe the Raptor 3 engines were not ready. Maybe SpaceX had changed the plan again. But the deeper problem was more uncomfortable. The rocket may have been closer to ready than the pad itself. That changes the meaning of the delay. It stops being a scheduling problem and becomes a systems problem. SpaceX was not simply asking whether Booster 19 could fire. It was asking whether Pad 2 could take the hit. And the first real answer came in seconds. The first wall appeared during a test that was supposed to be controlled. Booster 19 was not trying to fly. It was bolted to Earth, loaded with liquid oxygen and liquid methane, and asked to perform one brutal act. Light 10 Raptor 3 engines on the new pad and survive the first seconds. At first, it worked. The engines ignited. Thrust began to rise. The system seemed to be entering the narrow window where a static fire becomes proof that the vehicle is real. Then the pad called abort. Not the booster, not the engines, the ground system. Somewhere inside the web of sensors, water lines, propellant systems, and safety logic, a signal crossed the line. The computer did what it was designed to do. It commanded a fast shutdown. That sounds clean. It was not clean. A rocket engine is not a light switch. Inside each Raptor, turbopumps are spinning at terrifying speeds. Oxygen and methane are flowing under extreme pressure. Combustion is balanced inside a chamber that is already living near the edge of material limits. When a shutdown happens too violently, the engine is forced through an ugly transition. Valves close, pumps decelerate. Mixtures shift. Temperatures spike where they should not. Vibrations appear where smooth flow existed a fraction of a second before. In those seconds, a safety system protected the pad from uncertainty. But the engines paid the price. That is the first serious lesson of Flight 1-2. A rocket can be healthy, an engine can ignite correctly, the test can begin as planned. And still, the system can damage itself because the ground was not ready to let the machine breathe. The deeper system is not the engine. It is the decision-making machine wrapped around the engine. Modern rockets do not fail only when metal breaks. They fail when information becomes uncertain. A sensor vibrates loose, a pressure reading flickers, a water line reports something slightly outside its expected range. The rocket may still be fine, but the system no longer knows that with enough confidence. So it stops. That sounds cautious, almost simple. But in rocketry, caution has mass. It has cost. It has consequences. A fast abort can protect the launch site and still punish the engines. A gentle abort can spare the engines and still prove the pad is not mature. Every safety choice moves risk from one part of the system to another. This is why Starship is so difficult to understand from the outside. SpaceX is not just building a larger rocket, it is building a factory, a test range, a launch pad, a recovery system, a fuel system, and eventually an orbital refueling architecture, all while the design is still changing. Each improvement creates new unknowns. Raptor 3 may be cleaner, stronger, and simpler than the engines before it. But a better engine does not remove the violence it creates. It concentrates it. The plumbing must feed it. The pad must absorb it. The software must interpret the chaos without panicking too early or trusting the wrong signal for too long. That balance is almost cruel. Abort too late, and you may lose hardware. Abort too early, and you may damage the machine you were trying to protect. This is the hidden layer behind Flight 1-2. The delay is not just about fixing parts, it is about teaching an entire launch system how to survive its own power. This is why Flight 1-2 matters beyond one delayed launch. Starship is not trying to prove that one rocket can fly once. That part is difficult, but it is not the final ambition. The real goal is harsher. Make the largest rocket ever built, behave like transportation. That means repetition, not one perfect flight. Not one heroic launch after months of repair. A vehicle like Starship only becomes revolutionary if it can fly, return, be inspected, refueled, and fly again with a rhythm that begins to look ordinary. And that is where the pad becomes destiny. If every static fire damages engines, the system is too expensive. If every launch tears apart ground equipment, the cadence collapses. If every test requires weeks of rebuilding, then the future slows down to the speed of damaged steel, replacement sensors, and caution. This is the part that separates vision from infrastructure. Mars does not care about ambition. The Moon does not care about renderings. Orbital refueling does not care how powerful the booster looks on a live stream. Every future mission depends on a chain of events so precise and repetitive that failure in one unglamorous ground system can delay everything above it. A loose sensor can become a postponed launch. A pressure anomaly can become a damaged engine. A pad that cannot absorb its own rocket can become the limit of an entire space program. And that is the strange weight behind Flight 1-2. It is not just a test of Booster 19 or Ship 39. It is a test of whether Starbase can begin changing from a place of experiments into a machine of production. Because the future SpaceX is promising does not begin in orbit. It begins with the ground learning how not to break. So when Flight 1-2 finally flies, the important thing may not be the moment it leaves the tower. It may be what had to be understood before the clamps released. The delay is not a sign that Starship has become less ambitious. It is a reminder that ambition has to pass through pipes, valves, water manifolds, software limits, cracked hardware, and data that does not care what schedule anyone announced. This is the part of spaceflight that rarely looks heroic. No one builds a civilization beyond Earth with speeches. They build it by finding the weak point no one noticed, breaking something expensive, tracing the failure back through the system, and trying again with less ignorance than before. That is what Flight 1-2 is really showing. The rocket is not just fighting gravity, it is fighting scale. Every increase in power makes the hidden problems louder. Every new version of the vehicle exposes a new boundary. Every step toward reuse forces SpaceX to confront a colder truth. Going to space once is not the same as making space accessible. A single launch can be spectacular, A working transportation system has to become boring. And boring, at this level, is almost impossible. It means the engines light without damaging themselves. The pad absorbs the shock without losing its sensors. The water arrives when physics demands it. The software knows when to trust and when to stop. The ground survives, not once, but again and again. Flight 12 was delayed because that future is not allowed to skip the hard parts. It has to earn them. So the next launch will not just be a rocket rising over Texas. It will be a question made of stainless steel, methane, oxygen, and flame. Can the most powerful machine ever built by humans become routine? Or will the ground keep reminding us that leaving Earth is not the hard part? Doing it again is,